further maths year 2, further matrices. Right, take a look at these two transformation matrices here, A and B. What I'd like you to do, please, is I'd like you to find the invariant lines for each of those transformation matrices. So the lines that don't vary under these transformations. I'll just pause and see if you can find those for me. I'll give you the answers in just a minute. Okay, so well done. So if you haven't noticed, A is a reflection in the line y equals x. So the two transformation invariant lines for that will be y equals x and y equals minus x plus c. B is a two-way stretch by scale factor 2 in the x-axis and scale factor 3 in the y-axis. So the two invariant lines in that case will be the two axes themselves. So the y-axis and the x-axis. They would not vary under that transformation matrix. So what I'd like to do now is find any vector that are in the direction of the vectors of each of those invariant lines. So just to explain what I mean is, can you find a vector that works in a line or goes in the same direction as the line y equals x, and so on for all of them. So again, just pause if you want to, give you a minute to think about it. Okay, so a vector in the line y equals x. Well, y equals x travels straight up at 45 degrees, and the vector in that direction will be 1, 1. 1 across, 1 up will give you that direction. Y equals minus x plus c, so that's a line going 45 degrees downwards, so that could be 1 across, minus 1 down. So an example of a vector in that direction could be 1, minus 1. Okay, so let's look at this. This line just here, x equals 0, it could be any vector as long as the x value equals 0. So you could have 0, 1, 0, 2, 0, 3, 0, 6.7, it doesn't matter as long as the x value is 0. So the simplest example would be 0, 1. And exactly the same for y equals 0. The second vector for that would be 1, 0. As long as the 0 is for the y, it would be an example of a vector traveling in the same direction as that invariant line just there. Right, what I'd like you to do, please, is for each of these, find the transformation matrix itself multiplied by the vector in the direction of the invariant line. Let's have a go at figuring out that multiplied by that, then that multiplied by that, and so on for B. Okay, again, just pause. Right, let's see what you would have got then. So for A multiplied by the first vector would be exactly the same, no change at all. For the second one, A multiplied by that, does it have the same effect? Not quite. This one seems to flick around. So you get minus 1, 1. On this side, if you multiplied it by that, you would get, in this case, 0, 3. So 3 lots of it. And in this one, when you multiply it across, you get 2, 0. Quick look at those and write each of the answers you got as a multiple of the original direction vector. It sounds a bit confusing. So look at the answer that you got once you did the multiplication and think about what's the multiplying factor of that compared to that original direction vector. Okay, so I'll pause, give you a chance to do that for those 4. Okay, so let's see what you would have got. Well, the first one's unusual because it's exactly the same. 0, 1, if you're looking at this bit just here, 0, 1 multiplied by 1, 1, you'll notice it goes to exactly the same vector. So for that one, all I'm going to do is just put another 1 in. So it's one lot of it. Whereas this one, as you can see, they are clearly different. The two vectors are not the same. So in this case, how can I get from that to that? I would have to multiply by minus 1. But they are still the same vector. And you'd expect that because it was an invariant line. How about this matrix? Well, for this matrix, we can see that to get from there to there, you need a multiplying factor of 3. So we could take the 3 out, and it's 3 lots of 0, 1. Same vector. And so finally, for this one, as you can see, 2, 1, it's got to be a multiplying factor of 2. So we're showing that when you multiply your matrix by any of the vectors, you always end up with the vector itself and some multiplying factor. Now this is important. The actual vectors themselves, the ones that actually do this, the ones that are in the direction of the invariant line, because if it's any vector, it wouldn't always work. It only works for directions of invariant lines. Then we call them eigenvectors. So an eigenvector is a vector that doesn't change under a transformation. And the multiplying factor, the numbers in the front, those numbers are what we call the eigenvalues. So when I say they don't change, they do change, they can change, but they change to a multiple of that original vector. Okay. So if you just grab your notebooks, in your notebooks, what I'd like you to do is just take these notes about eigenvectors and eigenvalues. So given that M is a transformation matrix, V is a general vector, and lambda is some scalar quantity, so that will just be a single number, just a scalar quantity. Then we can say that if we get a situation where we have mv equals lambda v, then v is what we call an eigenvector of M. So if you multiply your transformation by this given matrix, given vector v, if you get some multiple of that v value out, then the v value itself is what we call the eigenvector. As I said, it doesn't work for all vectors. If it doesn't work for a vector, then that's not an eigenvector. I'll show you an example of that in a minute. The lambda value is a scalar quantity, it's just a number, and that scalar quantity is an eigenvalue of M. And we say it is associated with whatever the given eigenvector is, or corresponds to it. Just an important note as well for your notebooks. If in the situation like we saw a minute ago, you have exactly the same, so in other words, if that lambda value was equal to 1, it wasn't there, then that means exactly the same as what it says on the board. It is still a direction on the invariant line, but it also has the extra property that it is a line of invariant points. And you're expected to notice that. So any eigenvector definitely is a direction of an invariant line, but if it has an eigenvalue of 1, then it is also a line of invariant points as well. In other words, the points do not change. And the truth is, we've used that fact before in year 1 when we talked about invariant points, and we just used the fact that mv equaled v. So mxy equaled xy. So we did that a bit in our first year. Okay, so work out which of these vectors, okay, so those 4 vectors, is an eigenvector of the matrix A and B. So what I'd like you to do is just see if you can work out which of those 4 vectors is an eigenvector of the matrix A and B. And I'll give you a bit of time to do that. So if you want to pause, work them all out for me, please. And if you're not sure, you can have a look at the very first example. I'll do one for you, and then you can go on from there yourselves if you want to. Okay. Right, so here's the first example if you need it. So I'm going to look at multiplying the A matrix by 1, 1. And what I notice that when I do that, I end up with 4 minus 6. Now what's important here is you're noticing that that vector there is not associated at all. It's nothing to do. It's not a multiplier of that vector there. They are totally different vectors. So in that case, you can clearly say that because it's not a multiple, 1, 1 is not an eigenvector of 1, 3, minus 2, minus 4. Okay, so if that was the hint you needed, you can pause it, have a go at the other 3, with matrices A and B. What I'll do is I'll run through the answers to that in a second. Okay, so let's have a quick look at your answers then. So the first answer I got is looking at multiplying it by minus 1, 1. And if I do that, I'm going to get 2 minus 2. And just to confirm, are they a multiplying? Well, to get from there to there, I'm going to have to multiply by minus 2. And if I multiply that by minus 2, yes, I do end up with the correct answer. So this is a multiple. In fact, I could write it as a multiple with a minus 2 out. So therefore, minus 1, 1 is definitely an eigenvector of 1, 3, minus 2, minus 4. And the associated eigenvalue for that one would be minus 2. So you can confirm whether a vector is an eigenvector by using this technique. Okay, so let's just quickly do the others. If I did that one times that one, I get 3 minus 2. I think we can clearly see they are very, very similar. Just to confirm, yes, minus 1 lot of it. So therefore, that is also an eigenvector of that. Whereas the last one is going to be minus 1, 2. Gets me 5 minus 6. And that is not a multiple. So therefore, it is not an eigenvector. What's probably important to notice as well is that if you've got a 2 by 2 transformation, you only have a maximum of 2 eigenvectors. Now, in fact, if you're dealing in the real world, then we may have a real number system. You may have a repeated roots and you may have non-real roots. If you are dealing with the full complex number system, you always have 2 eigenvectors for every single transformation. Right, so let's quickly check B. So we got that one multiplied by 1, 1 would get us 4, 4. We would also have, which gets us 1, 1. We would have 3, 1, 2 minus 2 gets us minus 2, 0, which in this case is definitely not a multiple, so it's not an eigenvector, as the first one was. We've got 3, 1, 2, 2. Which gets us minus 7 minus 2, which is not an eigenvector because it's not a multiple. And then finally, no surprises, that one multiplied by that one gets us exactly the same. So therefore, it is definitely an eigenvector. But what's important about this this multiplier factor here, it is also going to be an example of an invariant line of invariant points. Okay, I've given you that as an example there. So in this one, we can convert it to an invariant line by just looking at the relationship between these two. So if x equals minus 1, y equals 2, that's the relationship for that. Y is minus 2 lots of x. You can check that by substituting those numbers in and you can see it works. So that's the relationship. So therefore, that's the equation of the invariant line. Now you can do that with any of these vectors to get the invariant line. But why this one's important is because the eigenvector was 1 that we saw here, it is also a line of invariant points. Okay, so they're all invariant lines if they're an eigenvector, but this one is an line of invariant points. So you can find eigenvalues for a matrix by rearranging it. So it's a little bit more tricky to actually find the eigenvalues and therefore find the eigenvectors of just a general matrix. So that's what we're going to look at now. So grab your notebooks, let's just go through these steps relatively slowly just to make sure you're happy with them. So the first step I've got is the matrix multiplied by the vector v minus lambda v equals 0. So if you look there, all I've done is just rearrange this slightly. I'm allowed to do that because these two will definitely have the same order. This one could be brought over, so therefore that has got to be true. And noticing that it equals the 0 vector here. Now, if I try to factorize it, because that's maybe what you're thinking, oh look, I can take the v's out, I can factorize. What I end up with is this situation. So I can take a v out. I'm very careful with where I put the v. I put it on this side because that's where side it's on. And I end up with a matrix minus a scalar. Now, as you know, you can't do a matrix minus a scalar because the order of those two things is different. That could be a 2 by 2, take away a single number. It doesn't work. Right, so don't think you can just factorize because you can't. But there's a slight way of being able to factorize. I can use the identity matrix. Now, just have a think about this. If you've got the vector v and you multiply it by I in front, that has not changed it at all. Like I said before, it's like in normal maths, if you multiply by 1, it doesn't change the number. It's the same with matrices. You multiply by the identity matrix, it's still exactly the same as what it was originally. So v the vector v is exactly the same as iv. Now why does that help us? Well, if I put iv in there, I haven't changed it because those two are the same, then what's going to happen is I can now factorize. I can now pull out the v value, same as I did a minute ago, but this time, because I've got iv here, this is an identity matrix. I'm allowed to multiply an identity matrix by a scalar quantity, because all that would happen is instead of having 1, 1, 1 and 0s everywhere else, I would have lambda, lambda, lambda and 0s everywhere else. But what's important is this identity matrix using here must be the same order as a matrix M. So if you're dealing with a 2 by 2, this will also be a 2 by 2. If you're dealing with a 3 by 3, this would also have to be the 3 by 3 identity matrix. And now that I'm allowed to multiply, let's take the next step. Now what's important to say here is that this the equation in this form, it's exactly the same form as the original, there's no difference, but that form there is really, really helpful for allowing us to figure out what the eigenvectors are. To do it, we need the eigenvalues first, but once we've got the eigenvalues, we're going to reuse this form. So you'll see this quite often. Okay, but for now, let's just carry on going. Let's find the magnitude of both the sides. So I'm going to find the magnitude of both the sides, and as I know, because they're equal, the magnitude should be equal to each other. So the magnitude of this side has got to equal the magnitude of that side. Right, let's break this down a little bit. Well, we know that we're allowed to separate magnitudes out, right, because it's just going to be multiplying by certain amounts. We notice this part just here is saying what is the magnitude, what is the size of the zero matrix. Now the zero matrix is just 0, 0, 0, and the size of that would always be just 0. So it has 0 magnitude, it has 0 size. We can separate this part out into the determinant of that part and the determinant of v. Now what's important to notice is that you've got two numbers, these are just numbers because they're magnitudes, multiplying together to equal 0. Now we know for a fact then that one of those two parts must be equal to 0. Now we know that can't be equal to 0, okay, because it is an eigenvector. And an eigenvector can't, by definition, be equal to 0. It has to have some sort of magnitude, some sort of direction. So that leaves us with the fact that the m minus lambda I is equal to 0. Now this equation just here is a really important equation, and it's what's called the characteristic equation. So the characteristic equation, this thing that we've just worked out, we've just shown how to get, is a really important equation that allows us to work out what the lambda value is. If you look at it now, it does not have a v value in it at all. So the eigenvectors have disappeared from that equation. We're left with a matrix that we're given, a lambda value which we're trying to figure out, and an I value which is just an identity matrix. Now, the way we'll work it out is once we've actually substituted all the stuff we know into it, it can be expanded to form a polynomial equation. And I'll give you an example of that in a minute. And then, as I said previously, once we've got the eigenvalues, we can then use that equation at the bottom, which was just a rearrangement of this top one, to help us find the eigenvectors. So let's have a look at an example. I want to find the eigenvalues and the eigenvectors of the matrix 2, 5, 1, minus 2. It's not an obvious transformation matrix, so you wouldn't be expected to just be able to guess what the transformations are. But what we can do is we can still work out the direction of the invariant lines by finding out the eigenvectors and the eigenvalues. So first thing I'm going to use is that characteristic equation. That equation, the m minus lambda I equaling 0, is the equation we're going to use to figure out what that lambda value is. Now let's put the stuff in we actually know then. So we know what the M matrix is. We know that. So we can definitely substitute that in there. We also know what I is. I is just an identity matrix. In this case, it's going to be a 2 by 2 identity matrix. So we can substitute that in as well. And notice that I've also multiplied the lambda value in there automatically. So lambda times 1, 1 would get me lambda, lambda, 0, 0. These two are the same, so I can definitely take them away from each other, which I've done here, and I know that equals to 0. Now this is just the determinant, and we know how to work out the determinant of a 2 by 2. We're going to do that times that, take away that times that. So that's what I'm going to do next. I can work out that multiply that, take away 5 is going to equal 0. Simple bit of algebra, just expand it, rearrange it, simplify it. Lambda squared minus 9 equals 0. So now we can solve that, and we know for a fact that our two eigenvalues for this matrix are going to be 3 and minus 3. So knowing the multiplying factor on its own isn't very helpful, but we can use this to figure out the direction of the invariant lines, because we can use this to calculate the eigenvectors. Okay, so we're going to do one at a time. We're going to use the formula m minus lambda iv times v equals 0. So we're going to do one at a time. The first one we're going to look at is lambda 1 equals 3, and then afterwards we'll look at lambda 2 equals minus 3. So we're doing both separately. So let's start with the situation where lambda 1 equals 3. Now for lambda 1 equals 3, again, I can sub everything in. Now that I've got an m, I've also got a lambda, I've also got the I don't know what the v is, but I do know that I can rewrite v. So just remember from previous lessons, v is exactly the same as x, y, 0 is the 0 vector, so therefore I'll replace that. So now I'm going to multiply this through. So I've got minus 1 times x, 5 times y, would get me minus x plus 5y equals 0, and the bottom one, 1 times x and minus 5 times minus 5y equals the 0 vector there. Notice that you could rearrange it. You could rearrange it to get you 5y equals x, and that will be your invariant line. The line 5y equals x does not change under that matrix transformation. So if you're asked to work out the invariant line, you can use it in that sort of format. It is also, like it says there, very common for these two things to be exactly the same. Right, exactly the same equations. So don't be surprised if that happens. It should happen most of the time. So we need to figure out though, we don't want the equation of the invariant lines. What we do want is we want any vector that satisfies that equation, then that can be used as our eigenvector. So the way to do it is up to you. Don't use 0, 0. That's the only one that, although it works in the equation, isn't going to be helpful as an eigenvector. But the other options could be doing something like, well, I'm going to let y equal 1. And if y equals 1, I can see that x would have to equal 5. That's an easy way to do it, but it's up to you. Any points that work in there could be used. So I've got 5 for x, 1 for y, just to confirm, yep, 5 minus 5 lots of 1, it does equal 0. So that would definitely be an appropriate vector. So that would be our eigenvector. Right, let's just repeat the same process to the other side, and therefore get our second eigenvector out. So we've got m minus lambda I times by v equals 0, same idea. This time we're substituting minus 3. Just check you're happy where these numbers come from. So you put in minus 3 in to this equation just here, because it's here. So we've got 2 minus minus 3 is where the 5 comes from. These two numbers don't change ever, because that would be where the 0 part is. But this one would have been minus 2 minus minus 3, which is where the number 1 comes from. Okay. So that's why that matrix there is different to this one, because it's different eigenvalues. So once you're happy with that, expand it. So I've got 5x, 5y equals 0, and then I've got 1x, 1y equals 0. And lo and behold, these two are identical. They're both the equations x plus y equals 0. So therefore I can just pick any vector that works in there. So I've picked the vector 1, minus 1. Of course, you could do it the other way around, minus 1, 1. Any vector you like. All your vectors will be multiples of those, so that should work. Okay, so we've done an example of a 2 by 2. 3 by 3s are always a little bit more tricky. So we're going to look at an example of a 3 by 3, but also I'm just looking at how the examiner could vary it slightly, how they could change the question. So in this question, they're checking two skills. They're checking, do you understand what an eigenvector is? And can you use your skills to figure out what the other eigenvectors are? So I want to verify. Now, while you're getting that down in your notebooks, just make sure that you're aware what the word verify means. So the word verify in a maths question means, can you check? It's like someone coming along and saying, this is the answer I've got. Can you check whether it's right for me? Okay, similar to what you did earlier on. Right, so if it was to show that, you'd have to ignore that and you'd have to get that answer out at the end. So it's a very different, just a slight different wording makes a big difference to how you approach the question. So I want to verify that that is an eigenvector of that matrix. Right, so let's have a quick look through. So that's what I'm going to do first of all. I'm going to check that the image of 2, 1, 2 under that matrix is also going to be a multiple of 2, 1, 2, so therefore it is an eigenvector. So it's very simple. Multiply it by 2, 1, 2, see what answer you get out. Oh look, I get 16, 8, 16. Oh, surprise, surprise, this is exactly the same, except it is 8 times bigger. So therefore I know, and I can confirm, that 2, 1, 2 is definitely an eigenvector for that matrix, and it has an eigenvalue of 8. Okay, so I'd write a short sentence, something like that, just to confirm that you understand exactly what's going on. So 2, 1, 2 is an eigenvector of M, and it has a corresponding or associated eigenvalue of lambda equals 8. Right, so I'm going to use the characteristic equation to find the other eigenvalues. So I've verified that, and now I'm going to determine the other two eigenvectors. So I'm going to use my characteristic equation. And this is why it's a little bit more technical, because you're dealing with a 3 by 3, so therefore you've got more work when it comes to the determinant. But let's just go through it, remembering how we work out a determinant. So it's going to be take that, then work out the determinant of its minor determinant here, then do the minus 2, remembering that it's minus 2 because it's plus minus plus. That's that and that and that and that. And then 4 lots of that minor determinant. So I don't mind how you do it. You can do it any way you like. You can go down, across, you can go middle row. It's up to you. It should always get you the same answer. As you can see, I've opted for the top row. So I've got 3 lots of that and that. Minus 2 times 2 is 4. I've got 2, which is where the minus 2 comes from, because remember it's plus minus plus. Lots of that times that and that times that. Plus 4 lots of that and that and that and that. Okay, so if you've forgotten how to work out the determinants, you need to go back over some of the previous lessons or the previous PowerPoints and just make sure that you are absolutely solid and understand where that comes from. Okay, right, it's down to you to do some number crunching. So you can pause and figure it out yourselves if you want to. I've simplified it slightly there by expanding all the brackets. It looks like a right mess. So let's sort out some of this algebra. We can see we've got some lambda squares, lambda cubes. It's no surprise it goes to lambda cubed. You're going to get 3 answers out. I've rearranged it onto the other side just to make it positive. It doesn't really matter. The one thing that you could use though is the fact that you know one of the answers to this is definitely going to equal 8, because you got that for that first question. So if that may help you, you can factorize the 8 out to start with. But again, I would expect you to know these skills from your first year normal maths, and you can use whatever skills you've got in your arsenal to be able to work out how to factorize it and therefore find the solutions. You can even go as far as using your calculators. So I got now that I've got lambda equals 8, no surprise for that, but the other 2 eigenvectors are repeated. I don't just write down just one of them, it does say we want 2 eigenvectors, so we'll write down lambda 2 equals -1 and lambda 3 also equals -1. You have 2 eigenvectors there which are absolutely identical. Right, so what I'm going to do is I'm going to use these eigenvector values to work out their corresponding eigenvectors. Now there's no point in me doing 8 because I've already done it. That's the one that got me the first answer. And I don't need to do -1 twice. I can just do -1 and just see what happens. See why it has a repeated eigenvalue. What does that mean? So, yep, so I just said, we've already know that the eigenvector value lambda equals x corresponds to that, so there's no point in worrying about that one. And both of these are equal to -1. So let's have a go at calculating the eigenvector for this. So I've got m minus lambda I multiplied by v equals 0. So what I'm going to do is I'm just going to substitute in the -1, and notice I've done a few steps there in one, and there's nothing wrong with you learning to do the same. So if you look, it's a matrix M minus lambda times the identity matrix. So it's -1, so it's plus the identity matrix. So if you look at this compared to the original, you can see it's identical, except instead of 303, you've added 1 to it. Okay, because it was adding 1 from there. So once I've got that, I can multiply it out, and I get this situation. 4x, 2y, 4z equals 0. I get 2x, 1y, 2z equals 0, and I get 4x, 2y, 4z equals 0. And what's important to notice just here is that all of those are exactly the same equations. Now this is the interesting fact. Because you had a repeated eigenvalue of -1, that refers to the fact that you've actually got what we call an eigenplane. Now, a way of thinking about this is it could be that that transformation has some sort of reflection in a mirror plane. So if you reflected something exactly the same as if you look in a mirror, that mirror is a plane, an eigenplane, and you're reflecting in that. Now, we don't really have to deal much about eigenplanes, but what we do need to do is we do need to find some eigenvectors, same as we would do normally. Now, the same as what we had in the previous situation, you can find any vector that works in here. Now, what's important though is because we've got two lambda values, two eigenvalues, we do need to have two eigenvectors. Right? And you can pick any vectors you like as long as they're not parallel. Okay, so that's an important fact. So make sure you just get that down in your notebooks. The eigenvectors can be any two non-parallel vectors that lie in that plane. So I make life easy for myself. What I would do is make x equal to 0. That's okay, as long as you don't choose y equals 0 and z equals 0 as well. If I make x equals 0, then I've only got to worry about these two. So that could be z equals 1, y equals -2, for example. That would work. Or you could do the same if you ignored y. Make y equal 0, and then x could equal 1, and z could equal -1. There's a whole host of there's an infinite set of different vectors that you could pick for this. Now you can pick any two. I'm picking those two. Notice what's important, they both work perfectly well. One's where x equals 0, one's where z equals 0. But what's important is these two are not multiples of each other as well. So they are both equations that work. You can check them yourself by multiplying it in your head. Do that times that. And they both work. And interestingly, when you both do them, they both come out as the negative versions of them. Okay, so it's important to make sure that when you get a repeated eigenvalue, you still have two separate eigenvectors for both of those. Okay, right, so I'm going to pause that part of the lesson just there. Gives you an opportunity to have a go at the exercise on 6E on page 143. So have a go at that exercise, and then once you've done that, then you can carry on the rest of the matrices lessons.